So we're going to work in section 9.7. 9.7 is going to discuss complex numbers. And complex numbers are kind of a fun topic, and it relates to something else that's kind of fun. And that's a subject called fractals. Now, this is one of the most famous fractals. It's called the Mandelbrot set. Mandelbrot was a Polish mathematician. And what I'm going to do here, if I can, let's see, where's the play button's hidden there. There we go. As this video rolls in, it's going to zoom into different parts of the Mandelbrot set. Now, if you remember what the original Mandelbrot set looked like, the original view, take a look at what we're zooming into. It's kind of this mirror image of what we started out with. Now, the video is going to keep on zooming in and zooming in and zooming in, but no matter how much it zooms in, we're always going to see the same characteristic shape, just at different levels. Now, I'm not sure the relative sizes of where you started and ended, but I've seen other videos of this in which you start out kind of zoomed out, and they make the analogy that if your original picture was a soccer field, then the last one would be the size of a proton, so extremely, extremely small. So we've zoomed in quite a bit here, and yet there again you see that shape of the Mandelbrot set. So, I mean, not perfect, but a pretty good copy of it. And the video goes on. I actually had to choose a very short one. I chose one that lasts about 2 minutes. But they've got some that go on for like 15 minutes and zoom into, a power of like 10 to the 1000th power. It's just crazy. It's like a Google and then some. So, just kind of fun to look at. And if you Google fractals, you'll see a gazillion different images of fractals. So after this one's done zooming in, I'll pull up a couple images of fractals. But these all relate to complex numbers. They're built on complex numbers. Now it looks like we kind of stalled. Like, gee, where's our Mandelbrot set? Well, let's zoom in some more. And yeah, I think I see where it's at now. So there it is again, at a relative microscopic level compared to where we started out with. So it's just pretty cool stuff. Let's see here. Let me pull up some fractals myself, and I'm just going to flash through these. Some of these are created more with Photoshop, and they're not as mathematical, but I mean, they're just cool. Just fun to look at these things. So, give you a little taste of it. That one's kind of cool. And some of these, especially the ones that are built on math, like this one, definitely have some math meaning behind it, but you don't have to know or appreciate that to enjoy just looking at these things. So, all right, here's some more here. And you can't hear it, but I can hear it in my headphones. They get some pretty funky music here. Maybe that'll appear on the video. All right, so if you can catch the lights, please, on the back wall. Oh, no, those are fine. Yeah, that's fine. Perfect. So all this relates to complex numbers. Well, we don't know what complex numbers are yet, but let's work on that. So complex numbers were first studied by a mathematician in about the 14th century or thereabouts by the name of Cardano. And he started playing with these ideas, and people didn't like it for a long time. So section 9.7, and where it comes from is a desire to solve equations. So let me zoom in a little bit and try and make that a little bit lighter. There. That's not so bad. So one equation you could look at would be x squared equals 25. And we'll play around with this more in the next section. But our idea in solving this, one way to solve this pretty quickly is just to take the square root on both sides. Now there's a positive and negative square root, so you get x is plus or minus 5. We get the same thing if we tried factoring this. But what if I had a slightly different equation? What if I had x squared equals negative 25? Up till now, what have we said about such kind of radicals here? What do we call them? Narn, yeah. Well, um, what mathematicians started experimenting with, like Cardano, was saying, you know what? Let's use this. Let's not throw out the square root of -1. Let's use it. And that -1 is going to get a definition. We're going to call I the square root of -1. Now, I ostensibly stands for the imaginary number. And for a long time, people, thought of it as the imaginary. Like, oh, you can't do that. It's imaginary. It's ridiculous. Well, it's not. This is actually a part of our real world. When you analyze things in electronics and in various areas of physics, you will use I as part of your answer, part of your work. So it has this unfortunate label, but it's stuck. So we'll use it. Now, how does it simplify things here? Well, that gives me plus or minus 5 times I. And that means you've got a nice imaginary solution, but it's a solution nonetheless. The important thing to know about I is what you get when you square it. What do you suppose I'm going to get when I square both sides here? -1. The squaring is going to cancel out that square root. And that's what gets a lot of work done for us, is that this is something that we can square to get a negative number. And that's where I becomes really, really helpful. So let's play around with some more of these radicals for a little bit. Let's take a look at problem number 18. Square root of -4. Well, when you have these roots that have negative numbers, I'd strongly suggest you start by splitting off -1. Just peel it right out of the radical and then simplify it. How would this simplify in problem number 18? 2i. Good. So 2i. We can and should do a similar thing with problem number 20. Square root of -11. Now I'm going to write this two different ways, but at first glance, when you start simplifying this, well, square root of 11 doesn't simplify. That's okay. You can simplify and should simplify the square root of -1. It becomes I. Unfortunately, sometimes people get a little bit careless in drawing the radical here, so that they actually extend the radical symbol over I. We will not be taking the square root of I in this class, ever, period. So don't write I under the radical. Make sure that it's out of the radical. In fact, it's probably safer to write it as I times the square root of 11. That way you're clear that the I is not under the radical. So I kind of prefer this a little bit, although standard notation is a little bit different. We'll talk about that in just a second. Let's try problem number 22. Square root of -28. Well, actually, we're going to break this up into 3 radicals. Can anyone figure out what one of them might be? All right, square root of -1. Let me put that here. Go ahead. Now 28. How would I break up 28? What numbers can I use to break up 28? Good, 7 and 4. I'll put the 4 out here and the 7 here. Kara, how would that simplify then? Yeah, 2i, and you're right, the square root of 7 is just going to stay there. So 2i times the square root of 7. Yes, sir. Just because I didn't want to put it behind the 7, for the same reason that I changed the order here. But, I mean, you could write this in any of 6 different orders, and it'd be the same. So, it's just aesthetically looks a little bit better there. Question? Okay. Yes, sir. That's fine, too. I mean, typically, the number part comes out in front of the I. You just got to be careful that you don't write it like this, that you don't accidentally extend that square root a little bit. All right, then there'd be a much different animal. Let's try problem number 26. Six times the square root of negative 49. Yeah. Now, what did you put first? I mean, did you put the negative 1 or did you put the 49? Put the 49? All right. So it's going to be 6 times 7 times I, or better yet, 42I would be the number that I'd be expecting for a problem like 26. Let's do one last one kind of like this, and that's going to be problem number 28. Negative the square root of negative 121 over 144. So, let's see. I'll leave the negative out front, but I'm going to break up the radical, and I can do that because it's a division. You can break it up as the quotient of those two things. Now, I don't know as though we need to really formally go through all this part of dissecting these things. Maybe you can just tell me, what's the square root of negative 121? 11, 12, and because we have the square root of negative 121, we're going to get 11I there. So, yay. The negatives don't cancel each other out. By the way, I think on your test you had a problem like this. You had negative the square root of negative 36. Now on the test, the right answer was narn, right? It's not a real number. But I'm sorry. Narn, rest in peace. We're done with narn. All right. We now have something that's replaced that. We can actually work with something like this. What would I get for negative the square root of negative 36? Minus 6i. 6i. Well, let's carefully look at it. Square root of, or negative the square root of 36 times the square root of negative 1. That negative doesn't disappear, right? I'll get a negative 6i. So negative 6i should be the right answer. Now that we understand a little bit more about the different sets of numbers. In fact, speaking of sets of numbers, I is part of, or helps form part of a larger set of numbers called complex numbers. Now, complex numbers look like this. They're going to have a real part and an imaginary part. So complex numbers look like a plus b times I, where a and b are real numbers. Now, these are the numbers that you're familiar with, and I is the square root of negative 1. So let me give you some examples of some complex numbers. 7 plus 2i, negative 6 minus 5i, pi plus the square root of 2 times I. How about just negative 8i, or 13 can be considered a complex number if you think of it as 13 plus 0i. So all the real numbers that you're familiar with are really kind of a special case of complex numbers where this coefficient of I is 0. So this is a purely real number. This is a purely imaginary number. You have what's called the real part, and you have what's called the imaginary part. And we tend to write these things as a plus bi in that order because in certain areas of physics, the real part and the imaginary part have definite applications. So you want to keep those things straight. Now I've already expressed the idea that, sometimes you can change the order here when you're dealing with the square roots, just to make sure that the I doesn't appear as though it's under the radical. So in a case like that, yeah, it's not a bad idea to write the I here. In general, though, this number is out front and I is behind. So this is a coefficient, and then you have I. I'm not going to mark you wrong if you write, say, -6 minus I times 5. Or, you could also write -5I minus 6. Those are all the same. But, I guess what I would encourage you to do is keep your instructor happy. All right? Just write it in the standard form as best you can. Our eventual goal in this section is to add, subtract, multiply, and divide complex numbers. Let's practice this a little bit. And we'll start with problem number 38. So, add, subtract, complex numbers. (38) looks like this. 8 plus 3i plus -7 minus 2i. And in some senses, this is going to be like polynomial addition. The idea is you're going to add up the like terms. So what are the like terms here? Well, that'd be the real parts here. What's 8 plus -7? 1. And then the imaginary parts. Now, as far as the imaginary parts is concerned, you're just going to add up the coefficients. So 3 plus -2 is also 1. So you can write one of two things. You can write 1 plus 1i, or you could write 1 plus I. I'd probably write that if I was writing it for myself on a test. If you wrote 1 plus 1i, that's fine too. Let's try problem number 40. (5 plus 3i minus 6 minus 9i). Now in its way, it kind of reminds me of a little part of a problem that was on your exam. You have to be careful when you're subtracting these things because you need to distribute that negative to both of these terms. In fact, that's how I'm going to start out. I'm going to write it as 5 plus 3i, so I'm just dumping the parentheses there, minus 6 plus 9i. But the important thing is that that negative sign has to distribute itself to both of these terms. So here and then here. So it's going to change both of those signs. When I combine like terms, Micaiah, what would I get, please? Negative. Go ahead. There you go. Thank you. So -1 plus 12i. Good. Let's try problem number 44. Thanks, Nikaya. Problem number 44. So a little bit different. We've got -7 plus the square root of -81. And then plus -2 minus the square root of -64. let's take care of these radicals right away. Did I copy it down wrong?
It's actually minus -2 minus 64.
Oh, I need a minus here? Oh, okay. All right, we can handle that. Let's see. It's just a little Photoshop real quick. There we go. Minus. Before I worry about distributing the minus, though, Lauren, can you simplify the square root of -81 for me? Just 9? 9. 9. I.
Yeah.
There you go. So 9i minus -2 minus, how about the other one?
8i.
8i. Good. So once you simplify that, you've written these as complex numbers. Let's finish this by distributing that negative. -7 plus 9i plus 2 plus 8i. What do I get when I add these things together? -5 plus, good, 17i. Nice. Let's try problem number 46. We're going to slowly, actually not too slowly, but we're going to slowly work our way into multiplying complex numbers. And number 46 is square root of -9 times the square root of -100. Now earlier I said that when you're multiplying, or excuse me, when you're working with the square root of a negative number, the first thing to do is to get rid of that negative underneath the radical. So I'll do it this way. Square root of 9 times the square root of -1. Square root of 100 times the square root of -1. Now maybe you could have done this without that step. Maybe in your head you could figure that out. But, you know, I'm thinking it's not a bad idea to take a little extra time with these and simplify them. So, Mitchell, what would the first one simplify as? Good, 3i. And someone for the second one, Lisa? 10i. What do I get when I multiply 3i times 10i? 30i squared. Does anyone remember what I said I squared was? -1, right? So I squared is -1, so I end up with -30. That's the correct answer here. Now, had you not been so careful, then you might have gotten the wrong answer. If you accidentally said, oh, well, -9 times -100 is the square root of 900, then you would have gotten 30 for your answer. So it does make a difference. You have to be a little bit careful when you're simplifying those. But let's do a little bit of work then with, yes? Well, the final answer is -30. That's what I'd be looking for. If you just left it as I squared, you lose a point. I expect you to simplify I squared. All right. In fact, one of the things we'll look at is simplifying other powers of I. But that'll be kind of like the last thing we cover in this section. So this was kind of a little warm-up to multiplying complex numbers. And that's the big thing we're going to work on next. It was also a nice reminder of something that we're going to need a lot. And that is I squared is -1. So we're going to multiply and then divide complex numbers. So multiplying complex numbers. We'll start with problem number 56. 2i times 7 plus 2i. Okay. So, let's see here. The multiplication is kind of implied. You've got this times that complex number in parentheses. So let's distribute that. If I distribute 2i here to both of these terms, Sidra, what would I get, please?
14i
Plus?
4i squared.
Perfect. 14i plus 4i squared. Let's keep going. Rachel, what do you remember about I squared here? So that's 14i plus 4 times negative 1, or better yet, 14i minus 4. And that's fine. There's nothing wrong with this. There is the keep your instructor happy answer, which would be to write it as the real part, then the imaginary part. So negative 4 plus 14i would be probably the way I'd prefer to see it. Again, the thing that I want to emphasize is make sure that you simplify the I squared. That's something I do expect. Let's try some more here. Let's try problem number 60. So 3 minus I times 2 plus 3i. What process do you think I'm going to have to go through to multiply the two complex numbers? FOIL. Good. Same as multiplying any two binomials. So first, outside, inside, last. You guys look pretty gung-ho, so don't let me stop you. Go ahead. Go ahead. Try and do this one. See if you can't simplify it. You're going to have to add up some like terms. You're going to have to simplify the I squared. But see what you can come up with. And if you finish that early and want to borrow a graphing calculator because it does some really cool things, then feel free. Krista,
Yes.
help me foil this out, please. What terms would I get?
6 and then 9i
Mm-hmm.
minus 2i
Good.
minus 2i squared.
It'd be minus 3i squared. Because it's like a minus 1 times a 3. That's all right. Perfect. So can I simplify any of this? All right, well, so the first thing that you might do would be to add together the like terms there. So I'll end up with 6 plus 7i. What's going to happen to the minus 3i squared term? Yeah, it becomes a plus 3. So there's really kind of two steps in that. It's minus 3 times negative 1, and negative 3 times negative 1 becomes a plus 3. There is one last thing that I would ask of you. Can you figure that out? Yeah, 9 plus 7i. All right, you've got like terms there, so 9 plus 7i. How'd you do on that first one, number 60? Good, good, I'm impressed. Usually I give a couple examples, but you seemed pretty gung-ho. Problem number 64 is going back to a theme you're going to see from most math teachers, I would think. They want you to practice squaring binomials. So 3 minus 2i squared. You can't take any shortcuts here. You can't say, oh, well, that's 3 squared minus 2i squared, etc. Foil it out. Write it as 3 minus 2i times 3 minus 2i. Mindy, can you help me work through the terms that I get when I multiply this out?
9
So outside then,
minus 6i,
and inside is going to give you
minus 6i,
the same. Good. And the last one,
minus 4 plus 4i,
minus times a minus would be plus
4 squared, I squared.
4i squared. Good. So when you're squaring out a binomial, you should always get these middle two terms to be the same. Now, does that add to 0? No. What's this add to? Good. So we have 9 minus 12i. What happens to the plus 4i squared? Minus 4. And if we combine like terms, good, 5 minus 12i. Now, those of you who heeded my advice to come get a graphing calculator will be happy. I'm going to show you a trick on your graphing calculators, but I still want to see the work on your tests. Is that fair? You can check it. You can check it real easy. So here goes. Let's do the problem we just did. So I'll type in a left parenthesis, and then a 5 minus, where was it? No, sorry. Wrong. I was typing in the answer. Left parenthesis, 3 minus 2i. Now the question is, where is I on my calculator? Well, it's right above the decimal point. So how would I get it if it's right above the decimal point on my calculator? Press the second key. So second, and then enter, or second and decimal point. Let's put a right parenthesis, and then hit the square key on the left-hand side of your calculator. And then press enter, and then ooh and ah. Ooh, ah. That's pretty cool. Look at 5 minus 12i. Not bad. You can and should check your answers on these things. We could have done problem 60 the same way. Nonetheless, I'm going to want to see a little bit of work. You don't have to show me everything, but some work to let me know that it's you and not just your calculator. Something. I need to see something. I don't think that many of us can do this to in their heads. So I would, I'm not sure what you want to show me, but show me something. I mean, if you just want to go from here to here, that's fine. But I don't know. What are you suggesting that you would do to solve it?
No, I was just asking because when it's negative in the middle, you always know it's going to be two negative that you add. So I just wondered if you could just avoid that.
I mean, there are shortcuts, but it gets a little trickier when you're foiling out a complex number because you've got an I squared term that's going to make that negative, and you're going to end up with a little subtraction at the end. So, yeah, I'd like to see something. If you just went here to here, I'd probably mark it wrong. All right, I want to see something. On the top of all your tests says, show your work and circle your answers. Now, when your problems get easy, if I gave you, say, 2x equals 6, I don't want to see any work. I just want to see the answer. All right. But when the problems are a little bit longer, I expect to see a little bit of work. All right. But it's good for you, too, because if you make a simple mistake, maybe you subtract these wrong. If you wrote on a 6 here instead of a 5, then I can look and say, oh, well, they just made a simple mistake, and take off a point. But if there's no work, and all I see is, 6 minus 12i, I have no idea how you got that. I can't even give you partial credit if I wanted to because there's no work. So it's in your best interest to show me a little bit of work so that if you do make a mistake, I can look through and spot it and say, oh, okay, here it is, and just, maybe take off a point or something like that. All right. Appreciate the question. Let's do a problem like this, 66. When you're working with complex numbers, like all binomial type expressions have what are called conjugates. So they want us to multiply a complex number by its conjugate. Well, in problem 66, the complex number is 5 plus 2i. Its conjugate is 5 minus 2i. So if this is a number, a plus bi is a complex number, then its conjugate is a minus bi. And vice versa. If you had a minus bi, its conjugate would be a plus bi. But your goal here in problem number 66 is to multiply the two complex conjugates. You should get kind of a surprising answer. There's a lot of nice simplification that goes on with this one. Yeah, still FOIL it. Can't be right? Is it too nice? Did it simplify too nicely? Let's find out. So 5 times 5 is 25 minus 10i plus 10i minus 4i squared. We agree on that much? Okay, good. So get some nice, yeah, isn't that special? Well, 0i is still 0. So yeah, you could write 0i and that's fine. I'm just going to let them cancel out. What happens to minus 4i squared? Becomes plus 4, so we get 29. Ooh, cool. That's actually a very useful result, and we will use that in a little bit. It was that simple, yeah. That's always going to happen. If you multiply a plus bi times a minus bi, you're going to get a squared minus abi plus abi minus b squared I squared. Now, those middle terms are always going to cancel out. What's going to happen to minus b squared I squared? How can I rewrite that? Good, plus b squared. If you take a careful look at this, is there any I left in this expression? No, it's all gone. So when you multiply complex numbers together, you're going to get a real number. There's not going to be any imaginary part left. Let's work on some division problems. Divide some complex numbers. We'll start with problem number 70. So 4 over 2 minus I. Well, if you remember earlier in this chapter, when we had square roots in the denominator, our goal was to get rid of the square root. We didn't like to divide by anything that involved a square root. And even though we don't write it that way, I is the result of a square root. So we don't like that complex number in the denominator. So I need to get rid of it. And my trick here is I'm going to multiply this expression by 1. The question is, what form of 1 do you think I can choose that'll help get rid of this complex number in the denominator? Very good. 2 plus I over 2 plus I. Basically, you're going to multiply both the numerator and denominator by the conjugate of that denominator. So you're going to change this sign, and that'll be your binomial term that you're going to use to help simplify this expression. Now in the numerator, I'll just distribute that. I'll get 8 plus 4i. In the denominator, you get some work to do with FOIL. 4 plus 2i minus 2i. Here's Mindy's favorite part, right? Because those cancel. And then minus I squared. what happens in the denominator? How does this simplify? Rhonda? What's going to happen with 4 minus I squared? Yeah, 4 plus 1. Perfect. And we'll go a little bit further with that. That's going to be 8 plus 4i over 5. And I'm fine with that as an answer. Now, as I mentioned earlier, because of various applications of complex numbers, sometimes authors or people like to write it like this. They want it separated. They want their real part and they want their imaginary part. So you might see it like this. But the trick in this that made it work is right up here, is multiplying both the numerator and the denominator by the conjugate of the denominator. I mean, if you at least wrote that much on a test, if I gave you problem number 70 on a test and you wrote that much, you get 1 point right there. Don't even have to do anything else. You're still going to get at least 1 point because you're recognizing you have to multiply by the conjugate. Let's try another one like that. Some questions? Yes.
So you got positive 1 because I is negative 1 times.
It's negative of negative 1.
And then you just wrote the negative that turns into positive 1.
Exactly.
Okay, I just
Appreciate the question on that one. Did you ever? Okay. Anything else on this one? Kyle?
All the time when you're dividing you're always doing the conjugate.
Yeah, you're always going to do the conjugate. So let's do another one kind of like that. Problem number 72. 2i over 3 plus 8i. So Kyle, what would I multiply this one by? Perfect. 3 minus 8i over 3 minus 8i. Now we're going to have a little bit more work to do because in the numerator, we're going to get an I squared. So there is going to be some more work to do. But see if you can at least simplify the denominator and the numerator a little bit. There's probably a little trick at the end that you'll need some help with, and that's okay. It's your first example on this. curious, we still got sound. Do we have sound still? Yes. Cool. Okay, so let's FOIL things out in the denominator. It's going to be 9 minus 24i plus 24i minus 64i squared. In the numerator, 6i minus 16i squared. As with all your products of conjugates, you're going to get some nice cancellation. We can also do some work with the I squared terms. That's going to be 6i plus 16 over 9 plus 64. So 16 plus 6i over 73. Now, a lot of you left it like that. That's fine. 6i plus 16 over 73. Generally, real part, then complex part, that's fine. And you can go a little bit further if you're checking your answer on, say, what's our WebAssign. They'll probably write it like this. They'll take the time to split it up. I'd accept this one. You don't have to worry about splitting it up for me. Let's do one last example like that, and then we'll do some powers of I, and then we can be done. So the last one that we'll do is problem number 76. And I think I'll just do that one up here. Unless, do you guys want the practice? Yes? Yeah? Okay. All right, well, let's see. 2 plus 3i over 2 minus 3i. Now let me at least get you started. Make sure you're in the right direction. What am I going to multiply by in both the numerator and denominator? 2 plus 3i. And what throws people off sometimes is that you've already got a 2 plus 3i in the numerator, right? That's okay. You still have to FOIL it out. You still have to simplify it. And it will simplify. All right, so let's take a look at this one. If you FOIL out the denominator, you're going to get that nice cancellation as before. FOILing out the numerator is not going to be much different. You're going to get the same terms, just the signs are going to be different. So it's going to be 4 plus 6i plus 6i again plus 9i squared. It's remarkable how many times that turns into a 0. It doesn't. They have the same sign, not opposite signs. You do get some cancellation here in the denominator. So 4 plus 12i minus 9 over 4 plus 9. If I combine like terms, I'll get negative 5 plus 12i over 13. Good question. The answer is no. When you add those, you don't add them. It doesn't become a square. You just add the coefficients. So negative or 6 and 6 gives me 12, and the units are I. I think you can do division as well as multiplication on your calculator. So again, if I gave you a problem like this, I would want to see the work. But if you do 2 plus 3i divided by 2 minus 3i, you're going to get some strange decimal answer, which looks very, very unhelpful. But if you hit the math key and turn your answer into a fraction, you get exactly what we got. Negative 5 plus 12i, both of those over 13. Nice. One last thing to mention on these. Are you pretty comfortable with all your operations for complex numbers? Add, subtract, multiply, and divide? All right. One tiny little thing left, and that is powers of I. Powers of I. And there's really a couple different approaches here that you can take. The important thing to keep in mind is I is the square root of negative 1. I squared is negative 1. So that's the important two things to remember. And I'll give you a couple different ways to work these problems. But I guess I don't know. I guess I prefer this one. That is problem number 90. Let's see. Let's not do 90 to start with. Let's start with problem number 92. Problem number 92 asks you to simplify I to the 22nd power. You look at that and go, that's a lot, right? Well, there's a trick, though, that you can use. We know what I squared is. So what if I was to rewrite this as I squared to some power? What exponent would I have to put on the outside so that together it would give me a 22 here? 11, right? Because 11 times 2 gives me 22. Now, what does that help? Well, that helps a lot, really, because I know what I squared is, right? What's negative 1 to the 11th power? Don't say negative 11. Be negative 1 times negative 1 times negative 1. Kara? Negative 1. Why negative 1 and not positive 1? Because you have an odd number here. If this was an even number, what would you get? You get a positive 1. So you're going to get a positive 1 or a negative 1 from stuff like this. So let's try another one. Problem number 96. I to the 200th power. Really not that much different than problem number 92. So I'm going to start out by writing this as I squared. Norman, I squared to what power? What should I put out here? No, these don't add. What do? Multiply. So 2 here and what here? 100. Good. So I squared is again negative 1. Negative 1 to the 100th power. Mackenzie? Positive 1. It's positive 1 because you have an even number of negative signs. They're going to cancel each other out. What if you had an odd number of negative signs? So if you had like problem number 90, I to the 19th power, well, that's a little bit more of an issue because this isn't a nice even number. But there's a quick way around it. When you multiply things with the same base, you add their exponents. So if I split off just one I to the 18th times I to the 1st, then I can work with the I to the 18th power. We're just going to kind of not really do much with the I to the first power here. But let's work with the I to the 18th. I to the 18th, I'm going to keep that I out here. But how can I rewrite I to the 18th, much in the same way I did with 92 and 96? I to the second raised to the 9th power. Okay. I to the second is -1. -1 to the 9th power is negative. So I'll get -1i, or if you just want to write -i, that's fine too. But the trick here was to just split off that extra unit of I. And let me give you one more example like that. Problem number 94. I to the 97th power. So this is kind of like all 4 different examples of things that can happen when you're working with powers of I. I'm going to first rewrite this as I to the 96th power times I. See if you can't finish it up. Rewrite I to the 96th power somehow, and then try and simplify what you're left with. Kennedy, how could I rewrite I to the 96th power? Good. And let's simplify that. Jamie, how would this simplify? Let's start in the... Good. So it becomes 1 times I, or better yet, just I. Yay. So that's the 4 different things that can happen. I'm going to show you a different way to do these, and you're free to choose whichever one you like, and I'd actually like some feedback from you as which one you like better. If you look at I is the square root of -1, I squared is -1, we can kind of play the same game that we did and figure out a little bit of a pattern here. I squared times I would be I cubed. So if I multiply this by I, I'll get -I. If I multiply by I again, so -I times I gives me -I squared, which is a negative of -1. In short, you start getting a pattern. You get I to the first power, let's just leave that as I, -1, -I, and 1. I to the 5th power, this pattern is going to start all over again. So I to the 6th power, -1, I to the 7th power, I to the 8th, it'd be 1 again. So if you wanted to memorize that sequence, then another way you could do things is based off where you're at in this sequence. Let's take a look back at problem number 94. So we had I to the 97th power. So where is that in this sequence? Well, let's take 4 and divide it into 97. That's going to go 20, 17, a 4, 16. Now I don't care how many times it goes in evenly. What I care about is the remainder. And the remainder is 1. So the remainder tells me that I'm at this spot in the sequence. So I get I. So if you want to work it based on the remainder, that's a different way to work it. I to the 22nd, so 4 into 22 is going to go 5 times with a remainder of 2, so you're at the second position in the sequence. So I to the 22nd would be -1. So both of them work. It's up to you what you want to memorize and how you want to work it. Any preferences for one versus the other? First method? First method? Second method, anyone? That's right. Okay. Yeah, second method works too. All right. Usually I don't get the time to show both methods. Today I did. Let me give you some homework. For homework, try 17 through 79 and 89 through 95. It might sound like a lot, but I'll give you a week to work on it, okay? I know. It's wonderful.